Right then, question 5, the last question, I believe. So this is about stationary waves. We've got a diagram here. Notice that we've got 1.2 meters labeled on the diagram, but that is not labeling a single wavelength. That looks like two wavelengths to me. So first question, state whether the following pairs of points on the string are vibrating in phase or in antiphase, or neither in phase nor antiphase. So points A and B we can see are between the same pair of nodes, so they are oscillating in phase with each other. Remember, this stationary wave, the points A and B will both simultaneously go from where they are currently positioned to that lower bit. They'll do that in phase with each other. So points A and C are oscillating in antiphase. There's a single node between them, so they are therefore completely out of phase with each other. They are in antiphase. How could you check this experimentally? So, typically this type of setup is vibrating pretty quickly. It's quite hard to see. So anything that slows down those vibrations to allow you to visually inspect it. So a couple of possible methods. You could use a high-speed camera. You could replay in slow motion to visually check, to visually confirm, or you could use a stroboscope. Strobe light. Stroboscope specifically is a strobe light with a variable frequency to make the string appear to move slowly. Hopefully that's enough to get me 2 marks. I mean, you shouldn't need both of these. It says briefly how you could check this experimentally, so hopefully either one of those responses is enough, but I will have to check the mark scheme for that one. Part B, progressive waves transfer energy through the medium, stationary waves do not. Describe one other difference. So the key difference between a stationary wave really and a progressive wave is about the amplitude. If we look at our stationary wave here, points A and B are oscillating in phase, but they're oscillating with different amplitude. So the amplitude varies along the wave. At the nodes, the amplitude is 0, and at the antinodes, the amplitude is a maximum, and it gradually varies in between. Progressive waves have the same amplitude at all points. So that is going to be the difference that I will suggest. Arguably, there's other differences in relation to adjacent points oscillating in phase or oscillating out of phase, or the distance between points that are oscillating in phase, but I think that is harder to fit into a short description for 2 marks. So I'm going to focus on the amplitude. Remember to phrase your answer as a difference. It's not enough to just say the amplitude is the same everywhere in a progressive wave. You have to also say that it varies in a stationary wave. This is probably more than I need to say, but the amplitude varies along the length of a stationary wave. Amplitude is the same at all points along a progressive wave. Arguably, you could say that the amplitude gradually diminishes as the progressive wave attenuates, but I don't think that'll be necessary for the marks. Okay. Explain then how the stationary wave can be thought of as arising from progressive waves. So we can treat this stationary wave as the interference between the progressive wave traveling that way and its own reflection traveling in the opposite direction. This wave can be thought of as interference between a progressive wave in the string and its reflection from the end of the string or from the pulley. Hopefully that's okay for 2 marks. Part C then, from the diagram, deduce a value for the wavelength. Let's go back to this diagram and have a look. As I mentioned earlier, the labeled 1.2 meters here, if we look at this, this is a node, so there is a whole wavelength and there's the next whole wavelength. So that 1.2 is equal to twice the wavelength. So the wavelength here is 0.6 meters. And there's only a single mark here. We don't have to show working for that, I don't believe, but just in case, I will put something like this. The pin is vibrating at a frequency of 50 Hertz. Calculate the wave speed. So this is simply C equals F lambda, so 50 Hertz multiplied by 0.6 meters. It's 30 meters per second. That's it, job done.